So here we go with what is actually our final lecture to end the course. We have just a couple of things left to talk about with sound waves. And we're going to talk about today an interference phenomenon known as beats and also talk about the Doppler effect. So two really cool things in terms of sound waves. But we're going to get started with, to end our last lecture, just a quick guest speaker. Listen to Dr. Sheldon Cooper.
Hey, what's Sheldon supposed to be?
Oh, he's the Doppler effect.
Yes. It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
Oh, sure, I see it now, the Doppler effect.
So I really do love that show. It cracks me up. Well, I might disagree that the costume is a good representation of the Doppler effect. I think it's more like Young's double slit. But Dr. Cooper's description of the Doppler effect is spot on. But we're going to come back to that. First, I'm going to talk about beats. So when we talk about beats, again, it's a phenomenon that's created by two waves that are nearly the same frequency. So they're very close to each other in every property, except their frequency is just a little bit different. So if we look at this image here, we can see where in first glance, those two waves look to be the same. But if we look more carefully, we can see that one wave, the lower wave, has a little bit lower frequency. The peaks are spread out just a little bit more. Well, when these two waves travel through the same medium at the same time, they interfere and they add together according to the principle of superposition. But something really cool happens. What happens is in some locations, like you see the red line I've drawn here, I know I didn't do a very good job with my finger, but where the red line is, the two waves meet constructively. Where with the yellow line, the two waves are going to meet destructively. So what happens is we wind up with a series of different types of interference, constructive, destructive, constructive, destructive, because of the slightly different frequency. Now I want to show you a neat analog of this concept of beats using regular household item, a couple of hair combs. But to do that, I need some backlight. So come with me. Let's go over here so that I can get my hands free. Yeah, sorry about that. I know it's kind of scary me being that close. So let's turn you towards the window. So we have some nice backlight. Now, what I want you to notice here is check out if I take these two combs, the gray comb and the red comb. Well, if you imagine the teeth of the comb are kind of like the wave or the sound waves, the compressions and rarefactions. And these two combs don't have exactly the same amount of spacing or the same number or the exactly same frequency or wavelength. But watch what happens when we overlap these two combs. Can you see that? Can you see how in some areas we can see through the two combs, but in other areas it's blocked off? Well, that's an example of beats, because in some areas the gaps are lining up, in other areas they're not. And it really becomes apparent if we move the two combs a little bit. So we can see that pattern shift. So again, a result of them being not exactly the same amount of spacing. Well, that's exactly what happens to these two waves. Pretty cool demonstration, huh? All right, let's get back to my desk. So who'd have thought two hair combs could demonstrate that physics phenomenon? But again, a great analogy to what's happening here. Very close to the same frequency. So when they add together, we get this really strange combination of interference. Well, that combination of interference, if we were to draw it, might look something like this, where you see that we have areas of very large amplitude where the constructive interference occurs, and they're separated by areas of very destructive interference, very small amplitude. Well, what does this actually do in terms of a sound wave? Well, the result of that is a variation in amplitude or loudness. So when the two waves are mixed together, we hear what's kind of like a wah-wah effect. Loud, soft, loud, soft, loud, soft. Okay, well, what does that sound like? Well, check out this little video I made to demonstrate beats. So I'm playing two guitar strings there that have been tuned to be nearly the same frequency, not exactly the same. Could you hear that wah-wah effect? Could you hear when the two strings were played? You kind of went loud, soft, loud, soft, loud, soft. Wah, 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 wah. So those are beats. And when you play, or when you have two waves that are nearly the same frequency, when they combine, we get this really special effect known as beats. Well, if I change the tuning on those guitar strings a bit, and maybe you heard me notice that I did that, how often we hear the beats changes, or the beat frequency. So when we get the frequency closer and closer together, the beats start to disappear. The number of beats that are heard per second is equal to the difference in the two frequencies that are being combined together, and we refer to that as the beat frequency. So you can see that the further apart the frequencies, the more beats, the closer the frequencies, the fewer. And in fact, when you're trying to tune a musical instrument by ear, you're not really listening for the time when the two sound the same. What you're trying to find is a point when the beats disappear. Now, if they're really far different, you won't get beats, but you'll be able to hear that difference. It's when they get close, you hear the beats create. And then as you get closer and closer, the beats get more and more drawn out, fewer and fewer beats per second, or a lower beat frequency. So a really cool interference effect known as beats, where we see a combination of constructive and destructive interference. All right, enough about beats. Let's get on to and talk about the Doppler effect. So now the Doppler effect is not an interference effect. As Dr. Cooper explained to us, it's due to relative motion. Well, in order to get into the Doppler effect, let's hear what exactly we're talking about. So listen to this example. So did you hear it? In the video, as the truck drives by the video camera, we can hear the sound of the horn seemingly change. As it's coming toward, the pitch of the horn, or the frequency that we hear, is one thing. As it drives by and goes away, recedes, it seems to change. We get that effect. That's the Doppler effect. Now, the Doppler effect, again, is that apparent change in frequency due to the relative motion between the source of the sound and the detector. Notice that it says it's the apparent change, because the frequency that's being emitted by the source never actually changes. In the example with the truck there in the video, the horn is putting out the same frequency of sound, the same pitch all the time. But it sounds different based on the motion of the source compared to the camera, the detector. As the truck approaches the camera, the pitch is different than when it leaves. And we can hear that transition. It goes from a higher pitch to a lower pitch. That's the Doppler effect. And it occurs because of the motion of the source. Well, as it turns out, it could also be the motion of the detector. If that truck were sitting stationary blowing its horn, and say somebody driving on the street the opposite direction approached, went by the truck and drove away, they would again hear exact same effect, the Doppler effect. A different frequency when they approach the truck compared to when they drive away. Now it happens for a slightly different reason, but the same effect nonetheless. Well, let's take a look at the Doppler effect in much more detail. Well, to understand the Doppler effect, we want to first talk about, well, what if nothing is moving? Well, if there's nothing moving, meaning the source and the detector are not moving relative to each other. Listen to this real quick from that previous video. So you heard in that video, riding inside the truck, where the detector and the source, the horn on the truck, are not moving relative to each other, the sound of the horn never changes. The pitch is always the same. Well, that's because there's no relative motion. In this image here, just from this little simulation I found, instead of using a sound wave, they're using a light wave. But we can see as the light pulses, it sends out waves. And notice that each time it does that, all of the waves are equally spaced apart, because each time a wave is created, it travels one wavelength in the time it takes for the next wave to be created. Since nothing's moving, no matter where you stand, all of those waves would sound exactly the same and be the same as what is emitted from the source. But when things start to move, things start to change. So let's talk about the source moving. Well, in that same simulation, if we let it run, watch what happens as the light starts to move. Notice that in the front of the source, the waves get compressed together. The wavelength decreases. Well, it's because as the source is moving in that direction, the previous wave can't get as far away from the source because it's getting chased down by the source. The source is closing down the distance in between the waves. So the wave gets physically altered by being compressed together. Notice on the back side, they get spread apart for just the opposite reason. The source is running away from or leaving the location of the previous wave. So the wave is traveling in one direction, the source in the other. It actually increases the distance between. So the wavelength behind the source increases. So how does that correlate to frequency? Well, what happens then, of course, is if you're in front of the source where the waves are compressed together, the wavelength becomes less. You hear more waves per second than are what actually being emitted. More waves per second means a higher frequency. So the pitch sounds higher because the waves have been compressed together. If you're someone sitting on the other side and the source is moving away, the waves get stretched out, which means you're going to get fewer waves per second or a lower frequency, and you're going to hear a lower pitch. So we have the Doppler effect when the source is moving. It can be a higher frequency or a lower frequency. It depends on where you are, where the detector is located compared to the motion of the source. And the wave actually physically gets altered. Well, by how much does it get altered? How different it doesn't sound? Well, it's going to look like this, where f prime is the frequency that is heard or detected. F, the unprimed one, is the frequency emitted from the source, times this fraction, v over v minus or plus vs. So v is the speed of sound. It is how fast is the sound wave traveling. Vs is the speed of the source. So if we know the speed of the sound, the speed of the source, and the emitted frequency, we can calculate what is going to be heard, both in front and behind. Well, that's why there's the minus plus there. So there's our equation for finding the Doppler effect. It's kind of complicated. Well, you know me, I like you to know where does that come from. So watch this derivation of the Doppler effect for the source moving. So this is a derivation of the Doppler effect equation when the source is moving. Well, the Doppler effect all comes about because of a relative motion situation. So let's kind of start there and say that the distance that the sound wave with respect to the ground travels would equal the distance that the sound wave with respect to the source travels plus or minus, depending upon the direction, the distance that the source travels with respect to the ground. Well, the distance that the sound wave travels is actually just equal to its wavelength of the wave that is emitted. Whereas the distance that it travels relative to the source would be the wavelength, we're going to call that prime, that's being sensed by the detector. Plus or minus the distance the source travels with respect to the ground. We're going to write that in terms of the velocity of the source with respect to the ground times the period at which the waves are being created, because that's the amount of time it would have to move between waves. Well, we're actually going to operate on this and be able to find the Doppler effect from this equation. Well, first thing we're going to do is we're going to replace our period with 1 over the frequency. Then we're going to replace our wavelengths here in terms of velocity and frequency. Well, the wavelength of the wave that's being emitted would be its velocity, the speed of sound, divided by the frequency, f. The wave that's being received would be, again, the velocity of sound. The velocity of sound is going to be the same whether the source is moving or not. The source is moving doesn't make the wave travel faster. Divided by the frequency being received, f prime, plus or minus, again, the velocity of the source with respect to the ground divided by the frequency being emitted, which is 1 over f. Well, now really all we're left to do here is do some algebra. We're going to multiply both sides by f. And then we're going to multiply both sides by f prime. Now I'm going to solve for f prime. I'm going to bring this term over to the other side. Notice it's going to become then a minus or plus. And factor out the f prime. Then I'm divide by that quantity. So we find that f prime is equal to f times the quantity, the velocity of sound, over the velocity of sound minus or plus the velocity of the source with respect to the ground. So notice it's a little bit different than our equation in the slideshow, where v is the velocity of sound and vs is what I was using here as the source with respect to the ground. There you have it. So what ultimately is that effect? Well, of course, again, as we move toward, the sound gets higher, a higher frequency. So notice that you would have to choose in the denominator the negative sign so that you could subtract and get a denominator less than a numerator. Whereas if it's moving away, you need a denominator greater so that you get a lower frequency, so you would use the addition. Notice the way it's written, minus over plus, looks a little bit bizarre, but it actually helps us to remember that we use the top sign when we're moving toward. So using this equation is a matter of knowing what goes where and which sign to use. So that is a source moving. Let's take a look next at the detector that's moving. Well, if we look at the detector moving, we can do this with a simulation also, although it's a little bit different. So check out this simulation. Now you've seen things like this before. Notice as the speaker creates a sound wave, it's spreading out and it's being detected by our pressure sensor. We can't really hear this, I can't see it. We're not gonna be able to see the effect except on that sensor. So as the wave passes that light gray pressure sensor, we can see the waveform that's created. Well, watch what happens as I take the black sensor and move it toward that source. So the black sensor is now the detector. Can you see that as I move the black sensor toward the source, that the frequency of the wave that's created in the pressure is greater than the frequency that was emitted? The waves are more compressed together. Well, that's because as you go toward the source, you're intercepting the waves more quickly than just standing there still. So intercepting them more quickly means a greater frequency. Notice in this case, the wave itself doesn't get any change. It's still the same. It's just that you're running into it, so you're receiving it more quickly. When I pull the black sensor out, notice just the opposite occurs. Now I need to be careful to pull it slower than at which the waves are traveling, but now the waves have to catch up to me. So I'm getting fewer and fewer waves per time, and we see a lower frequency being traced out in that pressure sensor in this case. So again, the wave itself doesn't undergo any changes. So we get the same effect, but for a different reason, because the detector is intercepting or running away from those waves. So how much does that frequency get changed? Well, let's check it out. The formula here looks very similar, but notice a big difference. The fraction seems to be inverted. Well, that's because it's happening for a different reason. All the symbols here represent the same thing. V subscript D, of course, is the speed of the detector. So check out the derivation of the equation for detector moving. Here's the derivation of a detector moving. Again, we're going to start off with our concept of relative motion. So the D for the sound with respect to ground is going to be equal to the distance that the sound moves with respect to the detector, plus or minus the distance the detector moves with respect to the ground. Well, the distance that the sound moves with respect to the ground, again, is its wavelength. Distance of the sound relative to the detector is going to be the received wavelength, lambda prime, plus or minus. Again, we're going to use the velocity this time of the detector with respect to the ground. And the period. Now this time the period is going to be the period of the wave that's being received because it's the detector moving, not the source moving. So t prime. Again, we're going to replace t prime with 1 over f prime. Let's replace lambda with v over f. That's the sound with respect to the ground. Lambda prime, again, the sound with respect to the ground over f prime, plus or minus detector with respect to the ground over f prime. Here, notice we can factor out our 1 over f prime. So we're going to multiply both sides by f prime, multiply at the same time both sides by f over the speed of sound. Distributing through the 1 over the speed of sound, and we get the speed of sound with respect to the ground, plus or minus the detector with respect to the ground, divided by the speed of sound with respect to the ground. So again, we wind up with the same result. A little bit different in the symbols that I used. We still wind up with the Doppler effect for the detector in motion. So we saw in the demonstration that, again, moving toward, you hear still a higher frequency. So in this case, we need to use the addition function so that we get a numerator greater than a denominator. When moving away, you hear a lower frequency, so we have to use the subtraction side. So notice it flipped from the source equation. But that's okay. Notice it still shows that the top sign gets used for moving toward. So we get the same effect, but for a different reason, and thus the equation looks a little bit different. Well, what if both are moving? What if the truck is blowing its horn moving in one direction, but the passerby driving the opposite? So both the source and the detector are moving. Well, that's actually pretty easy. It just gives us a general equation, which is a combination of the two. And it's going to look like this. Now, don't worry, I'm not going to derive this one for you. Notice that this works in every case. If the detector's at rest, put a 0 in for v sub d, and you're back to the source equation. If the source is at rest, put a 0 in for v sub s, and you're back to the detector equation. So this will always work, but it will also work if both objects are moving. Now, it can seem to be a little bit tricky. Then, well, how do I choose what sign to use? Well, it's really just this simple. Consider the opposite object to be at rest. For example, if we want to determine which sign to use for the detector, just consider the source to be stationary. And is the detector moving toward the location of the source or away from the location of the source? And choose the appropriate sign, as we've already discussed. Don't worry about, is it really getting closer or further away? The equations will take care of all of that. All you have to do is say, is it moving toward the location of the source or away from the location of the source? And choose the appropriate sign. Do the same thing for the source. Consider the detector to be stationary. Is the source moving toward the location of the detector or away? Again, don't worry about, are they getting closer or further apart? All of that is taken care of in the relative nature. Well, as we've seen, this is all about relative motion. And I want to point this out, and this is the situation we're going to limit ourselves to in this course, but I do want to point this out, that the speed of sound, once it's created, is the speed of sound. So in other words, if I'm driving down the street and blow my horn, the speed of the sound from the horn travels through the air at the same speed as if I were sitting still. It doesn't add my speed on. However, if the wind is blowing, all bets are off. If the wind is blowing, the medium that is carrying the sound wave is actually moving as well. So if the wind is blowing in the same direction the sound is traveling, it will move at a greater speed. So our v in our equation here is going to be something different. If the wind is blowing against the sound, the direction the sound is moving, it's going to slow it down. So we do have to take into consideration the nature of relative velocity, even for sound, not because of the source, whether it's moving or not, but because of the medium. Now, our equations are written specifically for still air, no wind, all right? The air's not moving. If we were to incorporate that situation, we'd have to do a modification. Our v here that represents the speed of sound would have to undergo a little modification to account for the speed and direction of the wind. So I just want to point that out to you, but we're not going to deal with that. We're going to stick with still air, the Doppler effect. Well, that's actually the end of our conversation here, but I can't just let you go just yet. I need you to answer a couple questions for me. So check out this question here, just giving you 6 situations and the directions or relative speeds of a source and a detector, and they're asking you to identify what's going to happen according to the Doppler effect. So take a few minutes, identify for A through F, is the frequency going to be higher than emitted, lower than emitted, or is it going to be the same as what is being emitted? Note that the arrows represent both the direction and relative magnitudes. The longer the arrow, the greater the speed. Well, thanks for answering that question. Bring that with you to the next meetup. One last question. In this question here, we've got a source, S, that big pink dot, moving from left to right. And what they ask us to do is rank the frequency of the wave that is being received, greatest to least, in those 4 locations, 1, 2, 3, and 4. So rank those locations based on the who's going to hear the greatest to least frequency. Now do it right at that instant in time. Don't say, well, as it gets further away, it gets closer to, things like that. Just right at that instant. And again, bring your thoughts about this question to our next meetup. Well, that ends it. That's it. That's a course. That was the last lecture. I'm just going to take us out by saying thank you all very much for your kind attention throughout the course of the year in all of our lectures. Thank you for all of your efforts to make this a successful class. I really have enjoyed our time together. I especially thank you for your continued effort during this time of remote learning, where I know there can be times when getting the motivation to do it is very, very challenging. But you did it, you stuck with it. So that's the end of our presentations. All we have left to do now is take our exams on our way out. As always, if you have any questions on this lecture or any other lecture, make sure that you take the opportunity to get those answered, and we'll see each other soon.